All right, guys, so let's talk about time of concentration. Does anyone remember what this is?
They're kind of the amount of time that water is in that watershed before it leaves the outlet.
Yeah, the kind of travel time it takes. So our learning objectives, let me just write these out first. Learning. Terrible, guys. So one, we are going to define time of concentration. Thank you, Dylan. And then we're going to relate that to the kind of design hydrograph, this hydrograph that we're synthesizing or making. We will then apply, I'm going to call it TR55. It's really kind of a compilation of methods, but I'll call it the TR55 method to estimate time of concentration. And then we'll also introduce and apply the what's called a rational method to estimate peak discharge. It's kind of like a quick and dirty way to get a peak discharge. The TR55 method, we're not quite there to get peak discharge. We'll finish that journey on Thursday. Okay. So we defined time of concentration, right? It is TC, right? And this is the time required for the most, we'll call it hydraulically distant point in the watershed to the outlet. And I should say the time required for water to travel from a runoff, right? Also known as the longest travel time. Not necessarily the longest distance, but the longest distance is going to get us close enough. So we'll just kind of take a look at that. Here's a funky watershed. Who can tell me what order this watershed is if we look at stream order? Do you guys remember that? One. So this would be 2, right? 2 1s come together, we get 2. 1 1. That's 2. So 2 2s come together, we get a 3. Okay, just a little practice. We'll keep practicing that. Third order watershed. All right, and we want to think about the water droplet coming from the most hydraulically distant. So we'll pick here. This looks like it's the farthest. So it falls on this ridge, and then it travels as sheet flow. We'll define these in a minute. So kind of shallow sheet flow, and then it kind of for a certain distance, then it becomes, I'll call that sheet, and then it becomes shallow concentrated flow, kind of like rills, and eventually hits a channel. And then once it hits that channel, we're kind of zooming, we're going pretty fast, all the way down to the outlet. So our time of concentration is going to be the time it takes to travel all these three different routes. And that's kind of a simplification, but it's how this method works. We think about it as three different routes. And our time of concentration is going to equal to the time we spend in sheet flow plus the time we spend in shallow concentrated flow plus the time we spend in the channel. We need to estimate these and then add them up, and we get our time of concentration. But then how does that time of concentration translate to an actual hydrograph? How do we relate this to the hydrograph? Well, let's look at that. So here's our hydrograph. Usually they kind of come up quick, and then they might tail off. So they might have like a longer tail than on the front side. That's our hydrograph. So we'll have time over here. We have discharge over here. Then we're also going to represent the hydrograph. I'll just keep it simple and just make it one little point input of rain. And so this is going to be our precipitation depth in inches. So we just get some unit of rain that comes in. And let's think about how we model rainfall runoff. You guys are working on your HMS models right now. You've created your design storms, right? You've estimated the rainfall depth associated with a certain frequency storm. And you've done all these little adjustments based on the point to area factor and the time distribution, right? So you've created a hydrograph. That's your kind of design storm. So that's really all we know. We don't know, we're kind of, that's our input. That's our, that's the one thing we know. And then the other things we know are the properties of our watershed, right? You know, the area, the slope, you're gonna estimate some of these parameters, the curve number, that sort of thing. So what rainfall runoff modeling does is it takes this rainfall input and it translates it into an outlet hydrograph. And what this time of concentration calculation does is it tells you this one number summarizes the properties of your watershed. How long is water going to spend in the creek? How long is it going to spend on some hill slope before it hits the channel? And so that one number, besides the area and the curve number, describes the kind of hydraulic properties of your watershed by all these flow paths. And what it does is it tells us the relationship between when that rainfall comes in and when we get this peak of the hydrograph. And this is the lag time. So it's the middle, the kind of centroid of your rainfall to the peak of your hydrograph. And then if we look at the point of inflection on a hydrograph where we go from concave, this isn't a perfect drawing here, but if we go from convex to concave, we have some point of inflection where that curve changes. That is going to be our time of concentration between that rainfall event and that point of inflection. This is kind of some theoretical thing, right? We talked about time of concentration would be a hydrograph that has you have a steady input of rainfall. The hydrograph comes up and then it flattens out because everything's in equilibrium. What's coming in is equal to what's going out, and you get that flat hydrograph. So we're never going to really see that. That's kind of a theoretical thing. So people relate it to the point of inflection. And the kind of rule of thumb of how do you get to what is the point of inflection, that's not really a super useful thing to know. And so we take a step to relate the lag time to the time of concentration. And this is just kind of an empirical rule. And the idea is we're not going to know the lag time ahead of time, but we can calculate the time of concentration based on that hydraulically distant point and relate it back to the lag time to this peak, this time to peak right here via this relationship. So that's where we're headed with this. All right, so I'm going to keep this watershed up here. I'll simplify it. Every time I draw a watershed, I'm worried I'm going to draw something weird or obscene. I don't know. So here it is. Here's our watershed. It's a simple one. And we will focus first on, I'll make this red. We'll first focus on sheet flow. So remember, sheet flow is that real kind of just it's a sheet of water. It's really shallow. And obviously you can see it on like a parking lot if it rains really hard. You could probably see it in the deserts. You're not really going to see this on a grassy area, forested area. It might not even exist in that kind of setting. So at the end of the day, this is an estimate, and we're going to use it to kind of roughly estimate how long it takes water to go across the land. So the first thing about sheet flow we need to know is that we only apply it to the first 100 to 300 feet of flow. 100 would be for a steep situation. 300 would be the maximum for a, we'll just say mild slope, hill slope. What's steep, what's mild? There's just rules of thumb, and you can take a look at the guidance document for that. And we have an equation we'll use. It's an empirical equation, like most of this is. So time of sheet flow in hours is equal to 0.007 N times L. We'll define those in a second. P2 to the 0.5, S to the 0.4. So a very clunky empirical equation. Let's take a look at what these are. Does anyone recognize N? I'll give you a hint. We learned it in hydraulics. Manning's N. So Manning's N, remember, this is the roughness coefficient. The higher the number is, the rougher the surface water is traveling over is. And so Manning's N could equal anything from 0.01 for pavement all the way up to 0.8 for like dense grass, brush. So a bigger number up here in the numerator is going to mean a longer time of flow, right? So rougher slows water down, longer time. L is our length of the flow path in feet. S is our slope in feet per feet. Just as long as it's just a percentage or a fraction. And then, not a percentage, a fraction. And then P2 is the 50% AEP rainfall depth in inches. I love these non-homogeneous unit equations, but that's hydrology for you. At least engineering hydrology, I should say. So it's a weird equation. There's a lot of different things we have to calculate. So you can imagine, and we'll actually do this and for this lab is to go, you'll say, okay, I think it's a pretty steep slope, so I'm just gonna do the first 100 feet. All right, so that's our L. I'll look at the ground cover. Maybe you go out and walk it in the field. Is it pavement? Is it grass? There's a table here, and that table is table 15.1. You can take a look at that. Here's a nice little definition of time and concentration. Here's that hydrograph. And there's different methods in here, I'll tell you right now. Like this equation just gives it to you, the time of concentration all at once, based on some stuff. So you could compare. I might have you guys compare. All right, 15.1, here it is. Manning's roughness coefficient for sheet flow, less than 1/10 of a foot depth. And they give a smooth surface like concrete asphalt. We have different fields, different grass types, range, woodlands. So that's our range of Manning's end values right there. And then where would we get this 50% AEP rainfall depth from? So NOAA Atlas 14, we could do that. Or we could, stream stats. In Colorado, they calculate all this stuff for you. Because behind stream stats in Colorado, they actually do this curve number method, the NRCS TR55 thing. So they'll calculate that for you too. And then slope, you know, dy over dx, right?
They calculate every flow path, every possible flow path?
They will just pick the most distant one. I don't know how that works. Yeah, I don't know how that works. Yeah, I haven't looked into how you automate it, because there's a little bit of a user, you know, artistic part of this thing. So yeah, there's a lot of assumptions that'll have to go into it. All right, that's sheet flow. Now let's do shallow concentrated flow. And how am I tracing this line right here? Obviously, I don't have any information, but when we do this together, we'll look at contours, and water is going to flow perpendicular to those contours. So let me just do some light contours here. So these are what the contours would look like, right? So that's how I trace my flow path. So we'll do shallow concentrated flow. And so the assumption here is that after 100 to 300 feet, the flow concentrates and starts to make these, you know, it gets a little deeper. You can kind of think of it as like rills. It's not in a channel, but it's more concentrated. And the deeper water gets, the faster it moves. So this is going to be a shorter time. And the way we calculate shallow concentrated flow, again in hours. So we'll start with length over 3,600 times V, right? So this is just a unit conversion thing. We're taking a velocity and we are converting it to a time. Feet and feet per second. But we need to calculate this velocity. What is that going to be? So we'll go to a nice table and we've got some empirical equations. Again, this is based on Manning's, and we say velocity is equal to some coefficient, which we can look up, times S, our slope, to the 0.5. And you'll recognize this part from Manning's equation. So all of this is kind of simplified Manning's equation. And S, again, is in feet per feet, or meters per meters. And we want to look at table 15-3. So let's take a look at that. So what this is showing you is just a very simple equation. It's this power law equation where you have velocity down here, slope up here. I might flip this if I were really, because velocity is our dependent variable and slope's the independent variable. But it shows you that you've got different kind of covers: forest with heavy ground litter, pavement down here. Somewhere in between, we've got grass pasture. It assumes some kind of depth for those. We're not going to know what that depth is. It assumes a Manning's roughness for those different land covers. And then it gives you this coefficient. So that K coefficient is going to be this number right here. Or you could use this figure. Either way, it's not a very hard equation to put a number into. So you estimate your slope along that pathway, and how do I know where I start and stop? Well, I need to see a channel there, and maybe that's something I found in the field. Maybe it's something I can see from aerial images, or maybe it's like a blue line that USGS has drawn on their topo map. They've identified this as a channel. So that's going to give me my length and then my slope based on the change in elevation between those two. Oh boy, this is getting complicated. All right, last step, where are we at? Channel, open channel flow. And obviously this is going to be the longest pathway. It typically doesn't take that long till you meet a channel. Open channel flow, I like that, open channel flow. If you guys end up pursuing hydraulics or hydrology in grad school, you can take a whole class called open channel flow. It's beautiful. Christian's like, sign me up. I took it at Georgia Tech when I was living in Atlanta, just a class, and the professor, his name was Dr. Terry Sturm. He wrote one of the textbooks, and he would complain about, he like spent all this time writing this textbook. It's a huge labor of love. Do you make a lot of money writing textbooks, do you imagine? That's kind of a leading question. I don't know. You don't make a lot of money writing textbooks. It's not, I don't know. The publisher ends up taking, textbooks are expensive. You guys know how expensive they are. Publishers end up taking most of the cut. So he's complaining about that in class. I just finished this textbook and people are buying all the knockoff versions, and I'm sitting there and I got my little paperback version that I got from like Indonesia, like not made for sale in the US. I'm like putting my textbook down. Sorry, Dr. Sturm. Appreciate what you're doing here. All right.
A math professor who like found his own books, just like crappy plastic money.
So he's like, this is my textbook.
And sold them directly.
Directly to the students.
It was only like $15.
Right. I don't know if that's legit, but I respect that. He's like, no textbook can really cover what I want to teach. I feel that way about hydrology. Okay. I don't know if I'm going to write a textbook though. So Manning's equation, and now this is Manning's equation in kind of its full form. You'll note that Manning's equation kind of pops up everywhere. The first two methods that we just covered have Manning's equation embedded in it in some way, shape, or form, the coefficient or a simplified version of it. Why do we do that? because it's around, it's easy. Hydrologists are lazy, or hydrology is hard and we kind of need a shorthand to do it. So that's kind of what's behind it. We're estimating all this stuff, so we'll talk about how to kind of be conservative in it all. All right, so main equation, V is equal to K over N, R to the 2/3, S to the 1/2. Does anyone remember what K is from hydraulics? It's a coefficient. Yep, so 1 for metric and 1.49 for British gravitational. So we're going to be in, US units, British gravitational units, so 1.49. This is our Manning's coefficient. Does anyone remember what R is? What's that? Did you say it? No, yeah. Oh, good question. Yeah. Reynolds number, no, that's pipe flow. There's Reynolds for open channel, but that's a little more complex. It's hydraulic radius, yeah, Jake. Hydraulic radius, which is equal to the area over the wetted perimeter. I'll draw a channel for you real quick. So here's a channel. Here's our wetted perimeter. And then our area, right, it's just a cross-sectional area of the flow. What's that? Yeah, it's just what's touching, that gets it drag, like what's touching the edge of the channel. So what could be slowing the water down? And then that's our slope, right? So that'd just be feet per feet. For natural channels, N is going to be different than what it is on the ground. Like if water's flowing on the ground. When you're flowing on the ground, it's much rougher. You got a really tiny flow depth. You got grass blades, rocks, sticks, all this stuff. So our N is actually going to be much lower, relatively speaking. And for natural channels, this is just kind of a very basic range for natural channels. If you're in a conduit, stormwater pipe, that's different story. Concrete is going to have a Manning's roughness about 0.013 or something like that for concrete. So how do we do this? This is kind of a big thing here, open channel flow. We're trying to calculate the hydrograph. And in order to calculate the hydrograph, we need to know all these flow depths. We need to know A and P and all these things. We know how much volume we have from the curve number method. We don't actually know the flow rate yet. And we're trying to use this method to calculate the flow rate. So what you end up doing, and you'll find out in HEC HMS, is you just make some real basic assumptions. You say, okay, it's a big flood, so I'm gonna say the channel is full. And I'll set my channel dimensions based on a real estimate of, what's the channel dimension maybe at midway in that watershed. I'm not gonna look at how it changes from a first order to a second order and on down. You could do that, that'd just be a little more complicated. For your reaches, and this is where this comes into play as well, is when you parameterize your reaches, is you have to figure out what's the width of the channel. I'm gonna call it a trapezoid, right? We'll make it simple. We'll call it a trapezoid. It's got a width, it's got some sort of depth, and maybe a 1-to-1 slope or something like that. So you really simplify the system and you make some big assumptions. And that, my friends, is how we calculate time of concentration. So I'll just remind you that time of concentration is, well, that was velocity, right? So we have to go from velocity to time in hours, but we already learned that. So time of concentration, again, is time of sheet flow plus time of shallow concentrated flow plus time of water flowing in the channel. And if we want to draw a real simple hydrograph, a triangular one, and we have our little hydrograph, our rainfall depth right here. So this is just some, precipitation, and this is Q and our time. And we want to know how long it takes to get from the centroid of that rainfall to our peak, which is our lag time. Well, we can say that our lag time is equal to 0.6 times the time of concentration. A big estimate, but it's what we use. So what have we done so far? Let's do a quick review.
Hey, Joel,
Yeah.
really quick. So what's that up there? I know it's a presentation, but I think you're like on the second bar.
Right here?
Yeah.
Yeah, so this is just a kind of a convention. Let me just erase that. I'll draw a little better for you. This is a convention that people use to draw precipitation or the hydrograph on the same axis or the same kind of chart as the hydrograph. So if we have Q right here for our hydrograph, right, and this is our Q peak, this would be, and I'll just kind of like draw it right here, this would be precipitation. So this is CFS, this is precipitation in inches, and I'm just drawing this on a graph that's upside down. I could draw it right here, right, and just have a secondary axis. But I'm drawing it here because this is kind of a convention that people use. You know, maybe you could think about it as rain falling from the sky, right? It's just a little confusing because it's going down.
So yeah, so does that time might start when it starts raining?
Yeah, yeah. And this particular parameter, the lag time, is between the centroid of your rainfall. I'm drawing it simply. I could draw this if it were like a hydrograph, right? The centroid would be somewhere over here.
The precipitation peak to the well,
Not the peak, the centroid. The precipitation centroid. How do you calculate the centroid? I'm not going to get into that. It's not like, we're going to keep it simple. Yeah. So that's why I've been drawing just one little bar, so it's simple to visualize. So let's take a look back at our kind of runoff modeling journey here. We started with the curve number method. And what did we estimate with the curve number method, Val? Remember we had the numbers for land cover. We put some rainfall on the lands. And then based on the curve number and that equation, we estimated. The what?
I don't know.
That's okay. Christian, do you remember? Yeah, so runoff. And that equation said Q, it's just the nomenclature they use, but it's the runoff volume. You know, that equation was in inches, right? And then we do depth times area to get volume. So that gives us our volume. Then we just did time of concentration. And what does time of concentration give us? Edgar.
it's 1 minute takes for the most distant point on the watershed to travel to the outlet.
And ultimately, it'll let us figure out how long it takes from when the rain falls to when we get our peak discharge, right? That lag time. So this is the ultimate parameter we're interested in, is that lag time, which will let us say, okay, my rainfall is now, the hydrograph that's going to come out of this watershed is going to peak at this time. So we'll just say, we'll call it T lag or time to peak. Okay. Now the next kind of crucial parameter we need is peak discharge, and we're going to use the unit hydrograph method, which we'll learn on Thursday. The unit hydrograph method says, okay, if I'm given a certain volume of rainfall, how do I distribute that over a hydrograph? Well, I know volume now, and I know my time of concentration, so I can use those two parameters then to spit out a hydrograph, a synthetic hydrograph, one that we kind of make up. And then that'll give us our peak discharge. The kind of last component of this, how high is that hydrograph?